स्लाइड शो करो ना जल्दी भैया, स्लाइड शो करो। करिए भैया। A very good afternoon to all of you. I am back again to discuss whatever was left over in the atomic structure that we discussed last week. And plus, we have to discuss a few more topics in detail. Say, for example, there was a query regarding Millikan oil drop experiment, which we used to calculate the charge of an electron. Last time, we couldn't discuss it. So, before we proceed, let me start up with that topic also that was asked last time, that is the Millikan oil drops experiment. It was between 1868 and 1953 that Robert A. Millikan, who was an American physicist, he was working with various aspects of electron, etc. And he, in 1909, basically determined the charge of an electron. He used a Millikan drop experiment for the same. Here you can see there are various components out here. There is an atomizer. The atomizer converts the oil into fine drops. Then you can see two plates, the positive plate and the negative plate. The positive plate is having a small hole inside so that the drops which are being formed by the atomizer, some of them are able to fall because of the gravitational pull. Now, there is a light supply, as you can see here. This light supply ionizes the gaseous molecules that are present, and when the gaseous atoms are ionized, apart from their ions, electrons will also be formed, and we know electrons are negatively charged. So these electrons basically, they bind with these, not exactly bind, they present themselves over the droplets of the oil molecules, oil droplets, and hence the oil droplets acquire negative charge. Now, once the oil droplets acquire negative charge, they will be attracted towards the positive plate. And when this occurs, this is a telescope through which the oil drops were observed, okay? And if we change, both these plates are connected to DC supply so that the charge remains the same throughout the experiment. And once we adjust this charge supply, we can suspend the particles as long as we want in this chamber, okay? So this is what he did, and when he carried out this experiment, he was able to find out the charge of the electron, and he said that the charge of these electron was basically 1.5 into 10 to the power minus 19 coulomb, somewhat around this value, and experimentally it is the value which is 1.60 into 10 to the power minus 9. So the value which Millikan gave was very much closer to the actual value, and hence this experiment was able to determine the charge of an electron very, very successfully. So this is what the Millikan drops experiment is. Now, basically, last time we talked about the structure of the atom. We talked about the various models of the atom, starting from a philosopher like Democritus. He gave the word atomos, that means indivisible, the smallest part of the matter which cannot be divided. Though his work at that point of time was ignored, because during his time there were various other philosophers, well-known philosophers like Aristotle, Plato, who believed in four elements, that is air, water, fire and soil. So the concept of atomos goes neglected for almost 2000 years till Dalton proposed the model, which again was on these similar lines, that the atom is the smallest particle, it is the smallest form of matter. However, later on with the discovery of electrons, as we all know and we discussed also last time, electrons, they were discovered by Thomson. He took help of the cathode rays, which were discovered by William Crookes, and he discussed the properties of the cathode rays and finally said that these rays are made up of negatively charged particles, that is electrons. Similarly, the protons also, They were discovered during that time only. And now once electrons and protons were discovered, which are a part of the atom, it was concluded that atom no longer is the smallest unit of matter, but we do have subatomic particles like electrons and protons. And hence, J.J. Thomson gave the plum pudding model, where we had the atom being a sphere of positive charge and negatively charged electrons are embedded in this sphere of positive charge. Okay, this is what J.J. Thomson gave. But Rutherford, who was working in Thomson's lab only, he studied the alpha ray scattering. He observed minutely the various properties of alpha rays and alpha particles, and he observed that most of the time the alpha particles, they were being deflected in air only. He tried to streamline it and formulated the alpha ray scattering experiment using the gold foil, where he observed that most of the alpha rays, they passed straight on. Few were they were deflected by a small angle, and very few were bouncing back by an angle of 180 degree. So he said that in between the atom, we must be having some positively charged portion, due to which the alpha rays are bouncing back and deflecting. And since very small number of alpha rays are being bounced back or being deflected by any other angle, so this mass of that positive body is very, very small. Moreover, since most of the alpha rays, they were able to cross through the atom straight away without any deflection, it means that most of the portion of the atom was empty. And hence, he gave a planetary model of atom where he had the positively charged nuclei at the center and negatively charged electron are surrounding and moving in fixed orbit around the nuclei, and the remaining space was empty. Now, the problem here that arises was that this positively charged portion, ideally, initially it was thought that it was only made up of proton, and hence the atomic number, which is also equal to the number of proton, should be the mass of the atom also. But experimentally, it was found out that the mass of the atom was, mass of the nuclei, was much higher than the mass, than the atomic number. That means there are certain other particles also which are present in the nuclei, which are having some mass, which is approximately equal to that of a proton, but zero charge, because as such, this body at the center was positively charged, which obviously is due to proton. This observation led to the discovery of neutrons, which were basically the neutral bodies, but having the mass almost equal to that of proton. Okay, so by this time we had the protons, we had the neutrons, both present in the nuclei, plus we also had the electrons revolving around the nuclei. Then this model is also known as a planetary model, because just like we have the solar system where we have sun at the center and the planets revolving around the sun in the fixed orbit, here also we had the nuclei at the center and the negatively charged electrons revolving around the nuclei. So it was nothing but a model which was similar to the solar system that we have in. But this model had a major limitation, and the limitation was, according to the theory classical mechanics, any body, charged body, which is subjected to acceleration radiates energy. Now, since electron being a charged body, when it was subjected to acceleration, it was bound to lose energy, and once electrons start losing energy, it will fall in the nuclei, and hence the electron will immediately merge with the nuclei, and thus the atom will collapse. So this model was not able to explain the stability of the atom. Moreover, the spectra also, because according to this model, it should give a continuous spectra because the electron is losing energy continuously. So the spectra should be a continuum spectra. I'll just show you how the continuum, what exactly do we mean by continuum spectra later in my presentation. But Actually, the spectra is not continuous for the elements, but in fact, the spectras, they are the fingerprints of the elements. That is, each element is having a unique spectra. No two elements will have the same spectra. So since each element was having a unique spectra, but according to Rutherford's model, all the elements should have the same spectra, which is nothing but a continuum. So Rutherford model had the major limitations. Firstly, as I've just discussed, it was not able to explain the stability of the atom. And secondly, according to it, the spectra of all the elements should be continuum, but actually it is not. So again, Rutherford model was to be discarded and there was a need for model to be introduced. But by that time, different type of works were done. Like we have the Newton's corpuscular theory, which says that the radiation is having particle nature. We also had Maxwell's electromagnetic theory, which says that the radiation is having wave nature. We also had the Planck's quantum theory, which states that the radiation should have the particle nature. Now there are various phenomena which tells about the particle as well as wave nature. One such phenomena which tells us about the particle nature of matter is photoelectric effect, though we have discussed photoelectric effect last time also, but I am repeating it and we'll be discussing it at a greater depth now. Now if you go back to the history, Hertz and Leonard. Actually, Leonard was working in the laboratory of Hertz. So now you can very well correlate. Basically, it was the work that was being done by somebody was carried by the other person working in the same lab. So similarly, in the case of the structure of atom, model of the atom that we have talked about, Rutherford's working in the lab of Thomson and so on. So it is basically the legend that was being carried on. So Hertz initially, he was quite convinced with the Maxwell's electromagnetic theory that radiation is having wave nature. And to some extent, he was able to prove also. But another scientist, Philip Leonard, who was also working in the same lab, he was working in slightly different direction. He said he basically observed the change in the emission of electrons when a metal surface was subjected to radiation. He kept on changing the radiations and he constructed a phototube. This is a phototube that he made. You can see there is a metal plate. These are the incident radiations, and Leonard basically kept changing the nature of these incident radiations on the metal plate. Once he did that, he observed two important things. He said on changing the intensity of the incident radiation, only the number of electrons that were emitted from the metal surface changed. Their energy remained unchanged. Secondly, he also said that there has to be a minimum amount of energy which is to be incident on the metal surface for the electrons to be ejected out. If the incident radiation is having a frequency lower than this minimum frequency, which we called as threshold frequency, electrons will not be emitted from the metal surface. However, if you look both these interpretation on the basis of classical theory, then on the basis of classical theory, with increase in the intensity of the light, both the number as well as the energy of photoelectrons should increase. But experimentally, it was only the number that was increasing and not the energy that was increasing. So that means that there is some problem in the interpretation or some problem in the usage of classical theory. In fact, Leonard won the Nobel Prize in Physics for the year 1905 for the same. Here you can see you have the incident radiation falling on the metal emits electron, the electrons moves into the opposite sides, and once there is a movement of electron, the electricity flow in the circuit. Again, Einstein also tried to interpret the same. Suppose this much is the amount of energy that is being supplied by the photon. But This much is the amount of energy that is required by the metal to release the electrons. Now, since the energy of the incident photon is less than the energy what is required by the metal to emit electron, in such a case, no electron will be emitted. That means if h nu is less than h nu naught, where h nu naught is the frequency of the what? It is the threshold frequency, the frequency below which the metal will not emit out electron. If the frequency or the energy of the incident photon is less than the threshold frequency, electrons will not be emitted out. However, if it is greater, suppose this is this much is the radiation that has been given in incident photon. This is the threshold frequency. Now, since threshold frequency is less than the frequency of the incident radiation, definitely photoelectrons will be emitted out. Now, as we all know, energy can neither be created nor destroyed. It can be converted from one form to another. So, the remaining portion of this incident radiation is given to the electron that are being emitted out and gets converted into the kinetic energy of the electrons that are being ejected out. And hence, he gave the relationship that energy of the incident photon is nothing but is equal to the threshold frequency plus the kinetic energy of photoelectron. That is, h nu is nothing but is equal to h nu naught plus half of mv square. Here also you can see h mu is nothing but is equal to h mu naught plus half of mv square. Okay. So he gave a new theory. Einstein gave a new theory of light. He said that the waves, the electromagnetic radiation, is made up of discrete packets. He also said that the energy of each packet basically is dependent on frequency, threshold frequency, and moreover, he also came to the same conclusion as Leonard did, that with intensity, with increase in intensity, it was only the number that is increasing, the energy remaining unaffected. And so he gave this mathematical relationship. For the photoelectron, you can calculate any parameter using this equation. If you want to calculate the kinetic energy of the photoelectrons, you can use this equation or what all. This is the graph of the photoelectric effect, that if you have kinetic energy on the y-axis and frequency on the x-axis, you get a straight line with the slope equal to h and intercept equal to the threshold frequency h nu naught. This again, the graph again is because of the basic equation that the energy of the incident photon is nothing but mu naught plus kinetic energy, or you can rewrite is that kinetic energy of a photoelectron is equal to h mu minus h mu naught. It is one and the same thing. This is what has been written here. So the slope is negative. From the slope, we'll get the value of h, which is a constant, and intercepts gives us the threshold frequency. Now, as I've just said, that we'll be discussing about the spectra also, because as such, according to the Rutherford's model, all elements should have a quantum spectra. But Bohr's model, which came into the picture, which is dependent totally on the Planck's quantum theory, which is dependent on the particle nature of radiation, particle nature of light, says that whatever transaction of energy takes place, it takes place in the form of packets, and energy of each packet is h mu. So each packet is of the energy h nu, and Bohr, on the basis of his postulate. What were the postulates? If we quickly recollect back the postulates that we discussed last time. Firstly, the electron will remain in the same orbit, and hence this is the stationary state orbit. The electrons will emit energy or absorb energy only when they move from one orbit to another. But as long as they are in the same orbit, they will neither lose energy nor absorb any energy. So we have the nuclei in the center, electrons revolving around the nuclei in fixed orbit. So as long as this electron remains here, It will neither radiate nor absorb any energy. It will remain here only. That is the stationary state. But if this electron moves from this orbit to the higher orbit, in that case, what will be done? It will absorb energy. Similarly, if the electron moves from the higher orbit to low energy orbit, in that case, energy will be emitted out or released. And hence, this postulate was able to explain the stability of the atom, which Rutherford was not able to explain. Another important postulate that he gave, that since this nuclei is positively charged, it will definitely attract the negatively charged electrons. There will be electrostatic force of attraction, and if there is no force to balance this electrostatic force of attraction, then again electron will merge with the nuclei. So he said that to balance this electrostatic force of attraction, there is another force which keeps the electron away from the nuclei, and that is nothing but the centrifugal force. He said that for atom to be stable, the electrostatic force of attraction between the nuclei and the electron is equal to centrifugal force. And once these two opposite forces are balanced, atom will automatically become stable. Then, since the Bohr's model was based on the quantization principle, it was based on the Planck's quantum theory. It also said that angular momentum of electron can not be any arbitrary value, but it will be an integral multiple of h by 2 pi. So another postulate that he gave was that MVR, angular momentum, is an integral multiple of h by 2 pi. So with the help of all these postulates, he was able to explain the stability. He was also able to explain the atomic spectra of hydrogen. Please mind that the Bohr's model was valid for one electron species, maybe hydrogen, maybe helium plus, maybe lithium 2 plus, and so on. But initially, he was able to explain only the atomic spectra for hydrogen atom. Okay. Now, according to that, he said that again, when, as we have just discussed, that when electron moves from one orbit to another, energy may be absorbed or emitted depending upon the shell from which the electron is moving, and the wave number for transaction is equal to the Rydberg constant 1 upon Ni square minus 1 upon Nf square. Okay, and the value of the Rydberg constant for hydrogen atom is 1.09673 centimeter inverse. Okay, so using these values, again we can do a lot of calculation here. We can calculate the wave number, we can calculate the wavelength, we can calculate what all things we want to use, what all things we want using this expression. Okay, now what happens is, here again I have shown this, that we have a photon. When this photon, obviously for an electron to excite, you have to expose the atom to some energy, maybe in the form of light or heat. So when a system is exposed to energy in the form of photons, the electrons get excited from one shell to another. And when this electron gets excited from a lower shell to higher shell, it is going to absorb energy. Suppose this is a kind of absorption that has taken place. Now, when the electron has already moved to the higher shell, it wants to come back to the lower shell. It is going to emit energy. This is an emission spectra. And as we have discussed last time also, these two spectras are complementary to each other. If we have a bright line here, all these are bright lines. There are corresponding dark lines at the same wavelength. Wavelength will not shift. The wavelength remains the same, but the only difference is if we have a light line in absorption, the emission will give dark line, and vice versa. See, this is what happens. We have the source as such. If we expose the source as such to a very high temperature, we may get a continuum like this. In the continuum, you may see there are no lines. It is a continuous region. There is no line. There is no band. But if we have bands and lines in between, it becomes the line spectra. So this type of a spectra was, according to Rutherford, every atom should have Every element should have this kind of a spectra. But according to Bohr, all these lines in the spectra which we are observing, they will have different value according to the element, and this is what we know as the line spectra. And since every element will have different wavelengths of these lines, we call the spectra to be the fingerprint of the element. Okay. Now, the reason why the atoms have, why different elements have the different spectra, and why the spectra is known as the fingerprint of different elements, is a very basic and logical reason. And that is, say for example, in hydrogen atom, we have various shells being placed like this. One, n is equal to 1, n is equal to 2, n is equal to 3. Now, actually what happens is the spacing, the energy gap between these shells is different for different elements. Okay, no two elements will have exactly the same energy gap between different shells. Now, if this gap is different, if the energy gap between two shells is different, automatically the energy transaction will also be different, and that is what is being reflected in the spectra. So it is because at the atomic level, different atoms have the different spacing of these shells, so the spectra of all these elements is also different. So hydrogen, we have already done the various series starting from Lehman, Balmer, Pastrom. Lehman is the series in the UV region, Balmer in the visible region, and rest all Pastrom, Brackett, Perfund, Hampfire, they are all in the infrared or the far infrared region. So Lehman series means electron moves from any level to n is equal to 1, or from 1 to any higher level. It is the same energy, but the only difference is that if it moves from higher level to n is equal to 1, energy will be released. If it moves from 1 to that higher energy level, energy will be absorbed. The magnitude will be the same. If Ni and Nf remains the same, the magnitude will be the same. It is only the sign that is going to change. If it is negative, energy is released. If it is positive, energy is absorbed. Okay, then we have Balmer series, which is the only series in the visible region where the electron moves from the second shell to the higher or vice versa. Then we have Pastrom, where the electron moves from the third shell to the higher or vice versa. We have the Perfund series, Hampfire series, and so on. The Brackett series, obviously, in between. These are the various wavelengths that we have discussed last time. That Lehman lies in 100 to 130 nanometer region, Balmer from 400 to 650 nanometer region, Pastrom from 950 to 1875 nanometer, Brackett from 2600 to 4050 nanometer, from 7600 to 10,000 nanometer, and Hampfire series if it is more than 10,000 nanometer. So even if we know the range, even if we are able to know the range in which that transaction is taking place, we'll get some idea about the type of the series, or we'll have some idea about the type of the energy levels that are being involved in the transaction. Okay, now move on to some questions. I'll give you 5 minutes to quickly note down the question and try to solve them out. So I'll just read the questions for you people. They're very small. They are just the MCQs. If an electron in hydrogen atom jumps from an orbit level N12 to an orbit 3, what will be the radiation that is absorbed as the wavelength of? They're all simple. The formula is already known to you people. Wave number we have just discussed is equal to Rydberg constant 1 upon Ni square minus Nf square. And this is nothing but is also equal to 1 upon lambda. So I think by using this relationship, it will be very easy to find out 1 by lambda and hence lambda. Yes, what should be the answer? Any response? A should be the answer. Very good. Now move on to the next one. Compare the wavelength of a photon produced from a transition from n is equal to 3 to n is equal to 1 with that of a photon produced from a transition of n is equal to 2 to n is equal to 1. This again is very simple and very logical. You just have to think over it. No calculations are required in second question. N is equal to 3 and 1. Obviously, if you arrange them as n is equal to 1, n is equal to 2, n is equal to 3. From 1 to 3, this is the energy gap level. From 1 to 2, this is the energy gap. Obviously, from 1 to 3, energy is larger than 1 to 2. Larger energy means lower wavelength. So 1, 3 will be lower wavelength than 2, 1. That means which choice? A again. Then third one. Light of wavelength lambda shines on a metal surface with intensity x, and the metal emits y electrons per second of average energy z. What will happen to y and z if x is doubled? X, Y, Z, they are just used to confuse you people. So sort it out intelligently. Intensity is doubled. Y, the number of electron is doubled, but the energy remains the same. This is what the conclusion of the photoelectric effect is. Then, what are the limitations of Bohr's theory? Bohr model could not explain the splitting of spectral lines in magnetic field. It could not account for multi-electron system. It could not predict the intensity of the spectral lines. It could not explain the fine spectra in the spectra of hydrogen-like species. Only the second is correct? I think all are correct. First is correct because Zeeman, Stark effect, they were not explained by Bohr's model. Multi-electron system, it is not applicable. It is only applicable for single electron species. Then again, the intensity of the spectral line, Bohr's model was silent about it. And the fine spectra, as we discussed last time also, when these lines, they were seen under high resolution spectrophotometer, the lines were actually seen to be actually the group of closely spaced line, and this explanation was not given by Bose but was given by Sommerfeld. And so all these four are the limitations of Bohr's model, and hence option number D is the correct option. Then true or false, Bohr's violate two fundamentals law, de Broglie's and Heisenberg's uncertainty principle. It is all true. This is just what we have discussed. Okay. Now, when we talk about Bohr's model, which was totally based on the particle nature, we were able to explain certain important factors which were not being explained by the previous scientists, like we were able to explain the stability of the atom. We were also able to explain the atomic spectra of hydrogen. But still, we were not able to explain many important things, as we have just seen from question number 4. Bohr's model was also having a number of limitations. Moreover, Bohr's model was totally based on the Planck quantum theory, that is the particle nature. But the radiation was also having wave nature. The radiation, the light also shows the various phenomena like diffraction, etc., which illustrates its wave nature. So, de Broglie, he said that like radiation, every matter is having wave nature as well as particle nature. So that is the dual nature of matter. Similarly, we have the Heisenberg's uncertainty principle also, which are working in the similar direction. But first of all, let us see what de Broglie had to say. He said that the de Broglie's wavelength is equal to h by mv or h by p, which is the momentum. And moreover, it says that this h by mv, it has nothing but it has come from the dual nature. Because when we talk about lambda, we talk about the wavelength. When we talk about wavelength, it is associated with the wave nature only. But when we talk about velocity, velocity is mainly associated with a particle. So this equation itself was a reflection of the dual nature of matter. So let us see what are the various numericals that can be sorted out on the basis of the de Broglie's equation. Question number 1. A neutron has almost 2000 times the rest mass of an electron. Suppose both of them have an energy of 1 electron volt. How do their wavelengths compare? Yes. What is the de Broglie's relationship? Lambda is equal to h by mv. Again, you don't have to do it mathematically. Mass of neutron is higher. ठीक है? High mass means low wavelength. What does that mean? That the wavelength of the neutron is smaller than that of the electron, and hence option number B. Which of the following particles moving with the same velocity would be associated with the smallest de Broglie wavelength? Yes. Hydrogen, helium, oxygen, nitrogen. Smallest wavelength means highest mass. Option B, because if you have hydrogen, helium, oxygen, nitrogen, out of the four, oxygen molecule is having the highest mass. Highest mass again means the lowest value of the wavelength. See, all these numericals basically, they are basically surrounded by basis of this equation only. They can be solved on the basis of this mathematical expression. There is no need to feed in the value of the various constants or the variables here. Now, all moving particles have wave properties described by the equation lambda is equal to h by mv. True or false? True. What is the wavelength of an electron? Mass is given traveling at the velocity this. This is a numerical. This you need to solve it out. डालो यहाँ values, करो solve. The value of wavelength you have to find out. M is given and V is given. H by mv. What is the value of the constant H? 6.626 into 10 to the power 34 joules second. It is important to know the units also, because all the units we need to work with SI units unless and until it is mentioned in the question. Mass 9.11 into 10 to the power minus 31 kg. And V is 5.31 into 10 to the power 6 meters per second. So the answer should be it's 1.37 into 10 to the power minus 10 meter. Okay? Okay. We move back to the fifth one. What is the wavelength in meters of a proton traveling at 255,000,000 meter per second, which is 85% of the speed of light? Assume the mass of the proton to be 1.673 into 10 to the power minus 27 kg. Here also it will be calculated on the same basis. Karo. Do we have to use the speed of light? It is not required. It is an additional information that has been given that the speed is 85% of that of light. You just use this value of velocity which is given, which is, can we write it as 2.55 into 10 to the power 10 to the power 8 meter per second. Okay, so velocity is 2.55 into 10 to the power 8 meter per second. M is 1.673 into 10 to the power minus 27 kg, and value of H is known to all of you, 6.626 into 10 to the power minus 34 joules second. And hence the value of wavelength can be calculated using the same expression. For this, the answer is 1.55 into 10 to the power minus 15 meter. Okay? Move on to the next. Calculate the wavelength. Now it is specifically being asked that the wavelength to be expressed in nanometers. That is, whatever value you get in meter, it is to be converted into nanometer. Of a hydrogen atom, the mass is given as 1.674 into 10 to the power minus 27 kg, and moving at 698 centimeter per second, moving with the velocity at, the word with the velocity is missing, so it is moving with the velocity of 698 centimeter per second. Another conversion that is required here is 698 centimeter per second to be converted into meters. That is 6.98 meter per second. So mass, okay, fine. It is already given in kg. Convert the velocity in meters. That is 6.98 into 10 to the 6.98 meter per second. And if you do that, you can easily calculate the wavelength. Convert that wavelength in nanometer. Karo fatafat. And please try to solve all the numericals. Okay, just do not try to just fill in the values and leave the numerical so that the baad mein ho jayega. Try to solve as many numericals as you can. Okay? Okay. The answer for this is 150 nanometer. 150 nanometer. Move on to the next one. An atom of helium has a de Broglie wavelength of 4.30 into 10 to the power minus 12 meter. What is its velocity? Mass is 6.64 into 10 to the power minus 27 kg. In this case, the value of lambda is given, the value of mass is given, h you all know. You can easily calculate the value of velocity, which is nothing but h upon m into lambda. ठीक है करो and Hmm. The answer for this is 2.32 into 10 to the power 4 meter per second. 2.32 into 10 to the power 4 meter per second. Okay? Move on to the next. Calculate the velocity of an electron. Mass is 9.10939 into 10 to the power minus 31 kg, having a de Broglie wavelength of 269.7 picometer. Here again, you'll have the same formula. You have wavelength is given, mass is given, you have to calculate V, but please be careful that the wavelength which is given here is given in terms of picometer. So first convert it in SI units, convert it in meter, and then use the value for the numerical. So what will be the value of the wavelength in terms of meter? It will be 269.7 into 10 to the power minus 12. Nano is done. Okay? Then move on to the next. Calculate the velocity of a neutron with a wavelength of 65 picometer. करके देखो 8th और 9th. A bit faster, please. As I just said, the more you practice, the more expertise you will acquire. Okay, so please do practice. Don't just put in the values and leave the numericals. Try to solve the numericals also. This is question number 8 or 9. 8th it is 6 into 10 to the power 6. Okay, 2 points, just recalculate it, but it is of the order of 10 to the power 6 that you are getting. Okay, that is more important. Even there is slight change in that value. Maybe that instead of taking 6.6, etc., we are leaving it to first place of decimal. So that also might bring a minute change in the values. And what about 9th? It is 6086 meter per second. The 9th was the velocity of the neutron with a wavelength of 65 picometer. Okay, move on to 10th. Calculate the de Broglie's wavelength of a Newton with the mass 1.67493 into 10 to the power minus 27 kg, moving at 1/500th of the speed of light. What does that mean? That velocity is equal to 1 upon 500 into 3 into 10 to the power 8 meter per second. Okay? So now can you just try it out quickly? For number 10th, the answer is 5.107 into 10 to the power minus 10 meter. Okay. Now question number 11 is slightly different and interesting one also. What is the de Broglie wavelength in nanometer of a molecule of Buckminster fullerene? This is nothing but the allotrope of carbon, that is C16, moving at a speed of 100 meter per second. Now this is something which requires a bit more of calculation in terms of the number of molecules that are present in 1 gram of fullerene and so on. So first what we'll do is, we all know that its molar mass will be, since there are C16, so it will be 16 into molar mass of one carbon atom. So 60 into 12.011. To be more precise, we can always take 12. So it comes out to be 720.66 gram per mole. Then mass of one molecule. It has been asked, the de Broglie wavelength has been asked for one molecule. So for one molecule, it has to be divided by the Avogadro's number, that is 6.023 into 10 to the power 23 molecules. So we get the answer of 1.19673 into 10 to the power minus 21 gram per molecule. Converted into kg, it will be 1.19 into 10 to the power minus 24 kg per molecule. So what will be the wavelength? This is the mass now in kg. Mass is known to you, velocity is given to you, h is also known. Now you calculate the wavelength. Okay? So in such cases, if molecules are given, the molar mass is to be calculated. The molar mass, remember, is it in grams per mole? You convert that into molecules per mole, because it all depends upon the question which has been asked to you. Had it been per mole, then we would have left it out here only. But it is per molecule, so we are dividing it by Avogadro number and then converting it into SI units, that is kg, and hence the wavelength can be calculated. Now since we have been asked to report the wavelength in nanometer, so you do the calculations accordingly, conversion accordingly. Okay? I think that is all. Okay. So the de Broglies, if you compare the wavelength of de Broglies with the basis of the various calculations that we have done, it can be concluded that the de Broglies relationship is valid only for microscopic object. I repeat what we discussed last time, that all the objects can be divided into two broader categories, microscopic and macroscopic. Any object which cannot be seen by a naked eye becomes a microscopic object. Object which can be seen by a naked eye is a macroscopic object, no matter how small, how minute the object is. Okay. Now, on the basis of various calculations last time also, we have seen that this relationship lambda is equal to h by mv. This wavelength is dependent upon the mass. If mass is large, wavelength is small, and vice versa. If mass is small, wavelength is large. If this mass is small, then the wavelength is large. For all microscopic objects like electron, it is a subatomic particle, a microscopic object, mass is very, very small. It is of the order of 10 to the power minus 31 kg. For all these microscopic objects with smaller value of mass, the wavelength becomes very high. High value of wavelength means that that particular object is mainly having wave nature. Okay, it is mainly having wave nature. Whereas if you look at a body of large mass I mean to say macroscopic objects, this value becomes so small, it becomes negligible, it becomes a value which cannot be achieved. That means such macroscopic objects will have a very small value or a negligible value of wavelength. That basically will reflect that macroscopic object will have negligible wave nature. Okay, so hence this dual nature is valid only, this relationship is valid only for microscopic object, because it is for microscopic object that this value of wavelength has a substantial value, whereas for macroscopic object this becomes negligible. Okay, so we'll keep this in mind when we talk about the Heisenberg's uncertainty principle. It is an important consequence of the de Broglie's relationship, where we had talked about the dual behavior of matter. It was given by Heisenberg in 1927, and according to him, it is impossible to determine simultaneously and precisely the exact position and exact momentum of a fast moving subatomic particle like electron. Here again, there are various important things that can be discussed, because whenever you talk about a particle like electron, which is very small in size, to observe that small particle or to observe that microscopic object, we need to make a light fall on that object. Now, since that object is very small, so the light which is falling on the object should have a wavelength which is comparable to the size of the object. Now, size of the object is very small, of the order of 10 to the power minus 31 kg is the mass. It is very, very small particle which cannot be observed by naked eye. It is a microscopic object, and hence to observe, to find out the position of that microscopic object, the light which is to be fall on that object should have a wavelength which is comparable to the size of that object. So the wavelength again will be very, very small. So when a light of this very, very small wavelength falls on an object, now since that incident light is of very small wavelength, so its energy will be very high. So that energy, that light that is falling on a microscopic object like electron will be so energetic that as soon as it falls on that electron, it will impart its energy to that electron, and electron will immediately get displaced from its original position. So either you can find out the position or the momentum, but you cannot find out both. And so he gave this relationship delta x, that is uncertainty in position, into uncertainty in momentum, that is delta p. Uncertainty in position is delta x, uncertainty in momentum is delta p is greater than equal to h by 4 pi. This momentum is nothing but mass into velocity. Now, since mass cannot be uncertain, it has to be a fixed value, it has to be a known value, into uncertainty in velocity greater than equal to h by 4 pi. On contrary, if we talk about a macroscopic particle, macroscopic object means an object which can be seen by a naked eye, an object which is having a high mass. So to look at that object which is having a high mass, you require a light of a high wavelength to fall on that object. High wavelength means low energy. So that energy that incident light is having will not be sufficient to change the position of that macroscopic object. So macroscopic object will remain wherever it was in the initially also, and hence both the position and the momentum of a macroscopic particle or a macroscopic object can be determined simultaneously and accurately. Hence again, this principle is valid only for microscopic objects. De Broglie is valid only for microscopic objects. Heisenberg's uncertainty principle valid only for microscopic objects like electrons. So both these principles valid on for microscopic objects like electron, and Bohr's model was violating both these principles, because according to Bohr's model, both the position electron, the position, the momentum, as well as the energy of an electron can be determined, because Bohr gave the mathematical expression for the determination of the radii of its orbit, for velocity of electron as well as for the energy in which the electron was moving. Bohr gave the mathematical expression for all these three. And once there is a mathematical expression for all these three, it means all the value can be calculated easily. But as we have just seen that for microscopic objects like electron, the Bohr principle hence is not valid. We have to take into consideration the de Broglie's dual nature of matter. We have to take into consideration the Heisenberg's uncertainty principle. And since Bohr's model was violating both these principles, hence we need to have a new model which is taking care of the dual nature, which is also taking care of the uncertainty principle, or in a nutshell, can we say that subatomic particles like electron, they are mainly governed by wave nature, because de Broglie's wavelength was valid for microscopic objects that we have already done. Electron also have dual nature, but they have mainly wave nature. Macroscopic object like us, we also have dual nature, but mainly particle nature. Okay, and because of this Heisenberg's uncertainty principle also, so ultimately we should have a model which is mainly based upon the wave nature of electron. Bohr's model was based on the particle nature of electron, but now the model that we should have should be based on the wave nature of electron, and that is what is wave mechanical model. And so after Bohr's model, we study the wave mechanical model. Okay, now let us do, this is nothing but the same that we have discussed. Microscopic objects to locate any subatomic particle like electron, we require a radiation of very small wavelength, maybe of the order of 10 to the power minus 10 meter. And such radiations are highly energetic, and when they fall on electron, they change the velocity and momentum of the electron when they collide with. So the exact position can be known, but not the momentum. Whereas for macroscopic objects, the radiations are required are of longer wavelength. Its energy is so small that it is not able to change the velocity and momentum of the object by collision, and hence the exact position and the exact momentum can be known easily and precisely. So both de Broglie as well as Heisenberg's uncertainty principle are valid only for microscopic objects, subatomic particles like electron, and hence the Bohr's concept of orbit was discarded in favor of orbital approach, and the quantum mechanical model was introduced. Now let us see some of the numericals on the Heisenberg's uncertainty principle. First one. The uncertainty in the momentum delta P of a football thrown by some footballer, Tom Brady, during the Super Bowl, traveling at 40 meters per second is 1 into 10 to the power minus 6 of its momentum. What is its uncertainty in position delta x? The mass is given as 0.40 kg. So we all know the uncertainty formula, uncertainty in position into mass into uncertainty in velocity greater than equal to h by 4 pi. And since it is greater than as well as equal, so when we do numerical, it is equal to h by 4 pi. In this numerical, we have to find out the uncertainty in position. Mass is given 0.40 kg. What about uncertainty in velocity? Sorry? The uncertainty in momentum traveling at a speed of 40 meters per second is 1 into 10 to the power minus 6 of its momentum. So what you have to do? First of all, you have to calculate the momentum. That is P is equal to M into V. Mass is given as 0.40 kg. Okay. Velocity is 40 meter per second. So you'll calculate the momentum, and uncertainty will be this momentum, whatever value you get, into 1 into 10 to the power minus 6. Okay? So uncertainty in momentum can be calculated like this. H you know, for pi you know, so uncertainty in position can simply be calculated. See, P is equal to mv, that is 0.40 kg into 40 meter per second. That comes out to be 16 kgs meter per second it should be. Then we have delta P is equal to what? Uncertainty is momentum into 1 into 10 to the power minus 6. Okay, momentum is 16 kg meter per second, so accordingly it can be calculated. And hence, P delta x is greater than h by 2 pi, or simply you can just calculate delta x accordingly, which comes out to be 3.3 into 10 to the power minus 30 meter. Okay, and continuation, you have another question. You notice there is 2 ml of water traveling on the football at the same speed and delta P. Calculate its delta X. It is in continuation. Try to understand this question. You notice there is a 2 ml of water traveling on football, maybe a droplet of water or some water around 2 ml for traveling on the football at the same speed and delta P. That means V remains the same, 40 meter per second. Delta P also remains the same, that is P into 1 into 10 to the power 6. Delta X needs to be calculated. But what about mass? You can assume the density of water to be 1. So you just convert 2 ml in kgs. That is 2 into 10 to the power minus 3 kg. Okay. Now mass is known to you. Velocity is also known to you. Delta P is known to you. You can simply calculate the uncertainty in position. You can just note it down. Just note the answer for the second one. Don't start noting down the answer for the third one. Okay. Okay, let's just move on to the third one. An electron in that molecule of water, again a continuation of what the previous two numericals were saying. An electron in that molecule of water traveling at the same speed has the same uncertainty in momentum. Calculate its uncertainty in position if the mass of an electron is 9.1 into 10 to the power minus 31 kg. Simple or difficult? So delta P is same. It is a continuation with the same delta P. It is in continuation with what has been previously said. Mass is given to you, velocity is same, delta P is same, which is being given to you. But the only difference is that here you have to see P. P for everything you have to calculate. P you have to calculate for question number 2 as well as question number 3. momentum is getting changed because mass is getting changed. But overall is that uncertainty is momentum is 1 into 10 to the power minus 6 times the momentum. So whatever momentum you are getting in both question number 2 and 3, that has to be multiplied by 1 into 10 to the power minus 6 to get the uncertainty in momentum. Okay, so momentum is getting changed because mass is getting changed. Initially, it was for 2 ml of water. So the mass was 2 into 10 to the power minus 3 kg. In this case, it is for one molecule of, for one electron for which the mass is 9.1 into 10 to the power minus 31 kg. So since the mass is getting changed, the momentum is getting changed. The momentum is getting changed and the uncertainty is momentum is 1 into 10 to the power minus 6 times whatever momentum you are getting. So accordingly, the uncertainty in momentum is also getting changed. And hence you can easily calculate the uncertainty in position. Okay, so in this case it is 1.5 meter. Okay. Now, the first question was pertaining to football. Mass of 40 kg, I guess. 0.40 kg. Okay? The value of uncertainty in position was of the order of 10 to the power minus 30 meter. Then we moved on to water of mass 2 ml. Mass is getting reduced. Now it has become 2 into 10 to the power minus 3 kg. But still, it is a macroscopic object like football. Still, it can be seen by a naked eye. Okay? Uncertainty in position is of the order of 10 to the power minus 22 meters. So does the uncertainty of the order of 10 to the power minus 30 meter or 10 to the power minus 22 meter carry any importance? This uncertainty is negligible or almost doesn't exist. So what does this indicate? That for these two macroscopic particles, there is no uncertainty in position. Uncertainty in position is negligible. That is, for both these, whether it is a football or 2 ml of water, the position as well as momentum both can be determined simultaneously and accurately. Now in question number 3, we have moved on to electron, which is a microscopic object which is having a mass of the order of 10 to the power minus 31 kg. For electron, the uncertainty in position is 1.5 meter. Isn't it a substantial value? So that means there is uncertainty in position that exists for a microscopic object like electron. So for a microscopic object like electron, either of the two, the position or the momentum can be determined, but not the both. So all these three numericals, we have decreased the mass from macroscopic again to a macroscopic body, but of a smaller mass, and finally to the microscopic object. And conclusion is the same that we have been harping on, that for microscopic objects, the Heisenberg's uncertainty principle is very well valid. Whereas for macroscopic objects, it is not valid. Okay. So this was question number 4. Comment on the difference in the uncertainty of momentum between ball, water and electron. How does the mass affect this value? Okay. So as such, so the relationship is direct. Okay. If you uncertainty in position, because mass will be in the denominator. If we want to remove mass from here, it will be in the denominator. So if the mass is very, very small, then the uncertainties will be high. If the mass is large, uncertainty will be small. Then question number 5. If the position of an electron is measured with an absolute accuracy, then the uncertainty in its momentum will be. Hmm. B, that is greater than h by 2 pi, h by 4 pi. Is that? What is the formula? Uncertainty in position, m uncertainty, or we can have position answer momentum की ही बात करी गई है. Uncertainty in momentum greater than equal to h by 4 pi. Now the question is saying that if the position of an electron is measured with absolute accuracy, what do we mean by that? Absolute accuracy means delta x is 0. So when delta x is delta p, we have to find out greater than equal to h upon 4 pi delta x. Now if this delta x is 0, won't it be infinity? 1 upon 0. It is infinity. That is D. Okay. Or had it been the other way around, that if the momentum of an electron is measured with absolute accuracy, then comment on the uncertainty in position. Again, it would have been infinity that way. Okay. So actually, this is what we have been doing. We have been decreasing the mass, or we have been decreasing the momentum. If you decrease the momentum, this was increasing. This is what we did in question number 1, 2, and 3. We have been decreasing the mass. Decrease in m means decrease in momentum, and hence delta V was increasing. Here we have decreased, and finally brought it to 0. Then this obviously will become infinity. An electron cannot exist in the nucleus, but a proton or neutron can exist. Justify. Why can't we have electron inside the nucleus? Have you ever thought of it? How do you know that it will become unstable? Can't we have nuclei being negatively charged and positively charged protons revolving around the nuclei? Can this be possible? Why not? The protons? Why are they having less weight? They are having more mass. Okay, they are very, very heavy, and hence in comparison to, but still proton is a subatomic particle. Still it will have some uncertainty, but actually what happens is, because it is heavy, its mass is 1856 times the mass of an electron, and doesn't move. So we say that it remains stationary in the nuclei. But at the same point of time, electron also cannot exist in the nuclei. This again can be solved out mathematically. See, we all know that the radius of the nuclei is of the order of 10 to the power minus 14 or minus 15 meter. And if electron is to exist inside that nuclei, then the uncertainty in the position delta x of that electron should be of the order of the size of the nuclei. That is 10 to the power minus 14 meter. If uncertainty in position is of the order of 10 to the power minus 14 meter, then what about delta P? Uncertainty in momentum. Uncertainty in momentum will be h upon 4 pi into uncertainty in position. Okay, so 6.62 into 10 to the power minus 34 divided by 4 into 3.14 into 10 to the power minus 14. That means uncertainty in momentum becomes of the order of 10 to the power minus 20 kg meter per second. Okay. Now, if P is the uncertainty in momentum of the electron, then the momentum of electron should at least be of the order of this much. If uncertainty is of the order of 10 to the power minus 20, then the momentum should also be of a similar order. And energy can also be calculated. Now here we have calculated the energy using relativistic formula, which says that E is equal to under root of m square. This question is of slightly higher level, and I have just given the formula for the relativistic formula for energy, and I'm deliberately avoiding the explanation for this energy term, which is a relativistic theory, because that you will study at a slightly higher state. But this question, it has been asked a number of times in various competitive examinations, so I have thought to include this question. Okay, the energy again can be calculated using this formula, the relativistic formula, under root of m square c4 plus p square 3 square. Mass, m is the mass of the electron, c is the velocity of light, p is the momentum, c again is the velocity. Substitute the various values and calculate the energy. Whatever energy you will calculate, you will get the answer in terms of joules. Converted into million electron volts, it comes out to be around 20. Now, if we are talking about if we talk about radioactive reaction, what is the difference between a chemical reaction and a radioactive reaction? In chemical reaction, the electrons are involved. But in radioactive reaction, it is basically the nuclei. So we do have beta emission in radioactive reaction. Beta emission is what? That electrons are being emitted out from the nuclei. If we look at those beta particles which are being emitted as a result of radioactive decay of a nuclei, then energy of those beta particles is somewhat around 3 milli electron volts. Whereas for the electron which are revolving around the nuclei, for them the energy is around 20 million electron volt, much higher in comparison to what a nuclei can have. So again, this shows that electron cannot be present in the nuclei. Okay, because uncertainty in position as well as the uncertainty in momentum, both are pretty high. Okay, is that okay? Just quickly copy the answer to this. Because if not completely, the question may be asked partially also, that can electron exist inside the nuclei? Okay, in that case, even if you avoid energy term, at least the uncertainty in position and the momentum should be, you should be able to calculate those values. Okay. That is all. If you have any query, questions, doubts, you are please free to ask. Any online questions? Is there any question from your side, students? This is which place? Which place? Okay. Please do ask if there is any question, doubt, query, whatever it is. Actually, centrifugal force, there are two different type of forces that are acting on the atom. One is the electrostatic force of attraction. Electrostatic force of attraction will be a force that is attracting the oppositely charged particles. We have electrons which are negatively charged and the nuclei which is positively charged. So obviously opposite charges attract each other. So it is a force which is responsible for attraction of these two, and that is electrostatic force of attraction. And there is a centrifugal force which says that the electron, since these two charged particles, they are trying to attract each other, so there is at the same point of time a force which is pulling the electron away from the nuclei, a force which is tending the electron to merge with the nuclei, and that force which is pulling the electron away from the nuclei, since it is acting opposite to the attractive forces, and since they are balancing each other in this case, we say that atom is a stable entity. Yeah. Yeah, any question, please? Sorry, we are not able to hear you clearly. The last question you mean to say, why electron cannot exist inside the nuclei? Is that the question that you want to ask? Which one? Which question? Sorry, we are not able to hear you. The last question, I guess, in this only. Okay, fine. Okay. The question was that electron cannot exist in the nuclei, but a proton or a neutron can exist. You have to explain it. Okay, now here, as we all know, that the radii of an atom is of the order of 10 to the power minus 10, and that of a nuclei is of the order of 10 to the power minus 14 or 15 meter. So if that is the radii and electron has to exist in that nuclei, that means the maximum uncertainty in position which the electron can have should be of the order of 10 to the power minus 14 meter only. If that is the uncertainty in position, then uncertainty in momentum will be what? H upon 4 pi into uncertainty in position. That comes out to be of the order of 10 to the power minus 20. Now, if this is the uncertainty or in momentum, that means the momentum is also of the order of somewhat closer to 10 to the power minus 20 kg meter per second. And when we have an electron with this much high momentum and velocity comparable to velocity of light, because this momentum is only possible, this uncertainty in momentum is only possible if we uncertainty in velocity is of the order of the velocity of light, which is 3 into 10 to the power 8 meter per second. If this happens, then even the energy can be calculated. Even the energy can be calculated using the relativistic formula, which the details of the relativistic formula I am avoiding, but it is this m square c4 plus p square c square whole under the root, and this comes out to be of the order of 20 million electron volt. Actually, if you wish, you can even leave it up to the delta x and delta p value, because the basic point in this question that has been expected out of you, that you should know that the nuclei, if the electron is to exist in the nuclei, it has to exist in an area, it has to exist in a space which is of the order of 10 to the power minus 14 meter. This energy portion, the relativistic portion, which I've given in the second half, is an optional portion. It is just to clarify your understanding further, because if you calculate the energy of electron using this formula, energy comes out to be of the order of 20 million electron volt. However, if you look at a radioactive decay of atom, that is, if you look at the beta emission, nuclei are giving us beta particles, which are nothing but electrons. Again, for them, the maximum energy that they can acquire is of the order of 3 or at the most 4 million electron volt. And since again there is a huge difference in energy, compare 20 with 4. It is this 20, the amount of energy when the electron is remaining, the uncertainty is 5 times in the actual energy. And hence we can conclude that electron in no case can exist inside the nuclei. That is all. Thank you so much. You were not having the monitor running.